I don't see anything wrong. So we are going to do, I guess we'll just get it going. Oh, okay. And finally, we will go open up this. There we go. Okay, so ladies and gentlemen, thank you for your patience in resolving those issues. It is my profound pleasure to be with you today for two very important talks. These are talks that in many ways have been months in coming, and it is fortuitous that a series of events conspired that I could give them on the same day. These are talks of great importance to our research group, talks of great importance to the field in which we're applying work. And the two talks center around an application of a method known as convergent cross-mapping, which is a technique to assess the presence and the strength of causal connections between two variables in a system using purely empirical data from those variables within the system. So given two series, time series X and Y, sampled at regular intervals, using this technique of convergent cross-mapping, first introduced by Sugihara et al. In the pages of Science, and since explained in several other contributions with greater detail and with extensions. With this technique, we're going to be able to take two time series, regularly sampled, and be able to assess the degree to which one of them causally influences the other. This assessment of causal influence is one that is not fundamentally statistical, but instead one that depends on the realities of and mathematics associated with dynamic systems. In order to explain this technique in the first lecture, and in order to explicate tips and sort of provide guidance within the second lecture, it's imperative that I explain a set of principles and concepts on which this technique is based. Because CCM, or convergent cross-mapping, is based on a series of concepts that build on one another to provide the key insights and the key methodology needed to undertake this assessment of causality. And specifically, what I'm going to be doing here is providing a brief review, because it's something all of you will have encountered, and I think most people who view this video will encounter, a brief review of the use of state space, or the concept of state space. Secondly, I'm going to be talking about extending that concept of state space to something called a delay embedding, which is a way in which we can reconstruct state space given empirical data without having an explicit model of the system that we're characterizing. Having purely data from a time series, we're going to see how we can take the data from the time series and reconstruct something that is diffeomorphic to, that is, can be mapped in sort of a continuous way to a representation of the underlying time series. Excuse me, of the underlying state space of the system that gave rise to that time series. So if that time series was generated by a dynamic system, we can peek, as it were, into the state space of that system through the use of this delay embedding technique. Next, I'm going to go from a discussion of that delay embedding technique to take on the fundamental ideas behind convergent cross-mapping themselves, okay? And I'm going to attempt to provide some concrete intuition for why convergent cross-mapping works, what some of its limitations are, and provide intuition for how it allows us to distinguish in particular between, on the one hand, causal influence from one time series to another, from merely correlation between those time series. Okay, that's this lecture. The next lecture, I'm going to be going on to provide a series of tips and guidance and suggestions for applying this technique that build on this lecture. Okay. So, ladies and gentlemen, I see that we are hamstrung by an issue with the bottom of the screen being cut off. So I'm going to see if I can frog this. Good, there we go. Okay. Okay, so I'd like to remind everyone here of the notion of state space, often called phase space. So given a dynamic system, given a system whose state evolves over time, whose situation evolves over time, we can define a state space for that system as an alternative way of depicting the evolution of that system over time from the classic one, namely time plots. So if we have a system which evolves over time, of course, in a classic way, we could draw out on a curve with time going here to the right on the x-axis. We could draw out graphs of the variables within that dynamic system. This is something we can do regardless of whether we happen to have a model of that system. We can simply characterize over time curves. And depending on what field you're in, this is very common. In electrical engineering, these might be graphs of voltage over time, for example. Within epidemiology, these might be so-called epi-curves over time with incidence counts, or perhaps their prevalence case counts over time. When we have a system whose state is evolving over time, whose underlying system is evolving over time, at each point it has a certain state that we can plot out over time. But state space is going to provide us with a different way of visualizing that same information in a way that will bring out other features of the evolution of a system. Specifically, state space takes the characteristics of the system in terms of its underlying state, and it creates a plot of it, of that underlying evolution of the system, where on this plot, each axis is associated with an element of the state of that system. So we might imagine, for example, a system which is composed of for example, some number of susceptibles, some number of infecteds, and some number of temporarily immune people on a graph like this. So here we have the number of susceptibles on this axis, infectives, and actually these two should be reversed. Let me just do that here. This guy should be over here, and this guy should be over here. And we could view the evolution of this system over time as the number of infectives rise, hence it's going along the y-axis here. As the number of susceptibles fall, it's sort of coming in like this. And then as the number of immune individuals rise, it goes up to this level. And in fact, they're temporarily immune, so some of them become susceptible again. And it ends up going towards a fixed point here. So this is a depiction of this same system as it evolves over time, where that evolution is captured in a trajectory, right? And at any one point in time, the system is at a point on that trajectory. So there's a certain number of infectives, a certain number of susceptibles is determined by the coordinate along the susceptible axis, a certain number of infectives determined by the coordinate along the infective axis, and a certain number of temporarily immune people determined by the coordinate along the z-axis, the ti axis here. And as the system evolves over time, as those state variables change, it arcs out this trajectory. Okay. So here, given run of the model, we'll define such a trajectory. We could, moreover, reason about a set of possible trajectories, as we'll see in a minute. Time here is implicit. In contrast to this graph of variables over time, here, time, it's sort of parameterized by time. There's no axis for time because the axis defines the state. Rather, at certain points, it's going to be going faster along this trajectory, and at certain points, more slowly along that trajectory, right? And for a nonlinear model, we can have a state space that's very rich, that can have multiple basins of attraction, multiple areas associated with attractors that suck it in towards a certain point or in a limit cycle or what have you. And often our interest in public health is in shifting things between basins of attraction, shifting from a situation where disease stays endemic to a situation where it dies out, for example. So this is another illustration of a state space that actually shows for any given point here in the state space where the system will go next. So if I were to start here, for example, I'll undertake this trajectory. By contrast, if I were to start here, or let's say right here, I would sort of loop around, I would shoot up here, just following the arrows here, and I would loop up and I'd sort of go down here probably and start approaching that place. If I were to start here, I would zoom down here and eventually make my way out here and then shoot up. Okay, so this is an illustration of state space that's a bit more rich in that it characterizes the evolution of the system for any given point using these little arrows, which are determined incidentally using the derivatives. At any given point in space, any given value for the values of SI and TI, we can determine what the flows are, and hence the derivatives, the net flow for a given stock, say I, and we can use that to illustrate how we're changing in I and the rate at which we're changing in S by similar principles. And when we have multiple basins of attraction, we may a slight difference in policy or a slight difference in original location or the amount of resources we bring to the situation can make the difference between an infection that takes off and the number of infectives or the number of or a case where it dies out, for example. Okay, now, this lecture is not fundamentally about state space per se, but I want you to reflect on those few essentials of state space. More than that, I'd like you to recognize that when we do have a state space like that, we may have a situation where the dimensionality, the intrinsic dimensionality of the trajectories arced out in the state space are that fully occupy the entire state space. Or we may have a situation where, in fact, realistic trajectories, only occupy a small fraction of the state space, okay? And a given trajectory that might look three-dimensional might actually be something that's of smaller dimension. And indeed, if in the field of complex systems, there's very well-documented cases of systems that nominally have a certain dimension, that at first blush or at a naive level might seem to be three-dimensional, but if you actually look at them more closely, they might have a dimension between 2 and 3, or for that matter, below 2. So for example, for this particular case of a nominally three-dimensional system, we in fact have only 2 dimensions exercised. Anyone want to say, why is this? Why is it there's only really 2 dimensions in here? There's a fundamental feature, which is a common feature in complex systems, that reduces the number of dimensions. What is that? Why do I say this is only nominally 3 dimensions, and in fact, it's 2-dimensional? Yeah, the total population is fixed. And so really, there's only, as we'd say, 2 degrees of freedom. By specifying S and I, it immediately implies TI1 here. It immediately implies the other stock. Really, there's only 2 elements of give in the system, only 2 elements of flexibility. The other is given by that. And in fact, if we were to plot out that nice fancy curve that we saw here from the right angle, what we would see is that that fancy curve is just on a plane. The other, one of these axes can be directly, the value at one of these axes can be derived from a constant, namely the total population minus the value along the other two axes. Okay, so state spaces have rich and interesting character. And often with a state space view, we can gather a great deal of insight in a system that might elude us with purely a time plot or purely time plots. I would note that this is true even when what you're dealing with is an approximation of state space or summary. Things like when you have an agent-based model, which nominally has a number of dimensions proportional at least to the number of agents times the number of states a given agent can be in. Often we will create state space plots where each axis is a summary across all agents of the count of agents who are in this state or that state or what have you. And we can view the evolution of the system as a whole within this kind of pseudo state space or aggregated. So state spaces are useful, but they're very useful constructs. And they're useful constructs for understanding models and for understanding systems. But today we're going to use them fundamentally in another way, in a way to assess the existence and strength of causality. And we're not going to be applying them per se to models. We're going to be applying them to real-world data, empirical data, data from observations of the world that will support insight into the generating system out there, which we might know only dimly about, where we only have a limited understanding of it. And in order to understand how we do that, we'll build on this concept of state space. And we'll deal with it in a very particular context. We'll deal with it in the context specifically of coupled nonlinear systems. Systems that are nonlinear, the whole is greater than the sum of the parts, and where there's multiple state variables, but where those state variables are not solitudes, rather they exist in a system. The evolution of one of the elements of the state of the system is coupled with the states of the other pieces of the system. Okay, so very typically in complex systems, we'll have several elements of state. Maybe it's count of people are susceptible, infected, and recovered, or number of mosquitoes who are in each of those states, number of birds in each of those states, and number of people in each of those states. And these are tangled together because, say, people catch West Nile from mosquitoes, and mosquitoes catch West Nile from birds, and birds catch West Nile from mosquitoes. And we have this coupling between the pieces of the system. You're not going to get any infectives unless you have susceptibles mixing with people are already infectives. You're not going to get new infections. So there's this entangling of these different variables within the system. Within this context, we have a dependence of the evolution of one state variable on the other state variables, right? So the number of new infectives, which forms an inflow into infectives, number of new infections, the rate of new infections, which forms an input into infectives within an SIRS model, for example, is dependent on susceptibles and as well as the number of infectives, as well based on the prevalence within the whole population, potentially on the number of recovereds as well. In a predator-prey model, as we'll see, the evolution in the prey is influenced by the number of predators around. And the number of predators and their reproduction rate is dependent on the number of prey around. In a model like the Lorenz Attractor, the evolution of X depends on Y and Z and vice versa. Okay? So within these coupled systems, we have interdependence of elements of state, or the evolution of a given state variable depends on the other elements of state, or many of the other elements of state. Okay? Now, this fact is not merely a curiosity. It's going to have profound significance in making CCM possible. It's going to have profound significance in the motivations for undertaking delay embedding and constructing, as we say, shadow manifolds. So the deal here is that, look, the fact that the evolution of a given variable, say the evolution of the number of infectives, is entangled with the others, say the number of susceptibles, tells us what it means is that if we were to look at the number of infectives over time, that number of the number of infectives over time encodes information about the history of other variables. For example, if we see lots and lots of people being infected right now, new infections taking place, it tells us there's probably a lot of susceptibles out there. If we see the number of prey plummeting, it's probably because there's a lot of predators out there eating them. Okay? And what this says is, given the trajectory we see, the values we see over time of a given variable of the system, tells us about the value, the other parts of the system. It whispers for us. It whispers about the sort of the state of the rest of the system because it's tangled up with it. It's so affected by it causally that it tells us a lot about what's going on there. Okay. Much as just the other day, I was driving Australian visitors to the airport, and we happened to know about a water main break in the next street over, the next big street over. And I was going to a street and I saw a huge line of cars sort of coming down the other way. And I realized, oh, okay, that's probably because those cars are being diverted from that other street. So even though it was a different area of the city, a little bit removed, I knew, okay, this is telling me something about what's going on over there. And it's like that with these systems, okay? But this doesn't have to depend on faith or merely common sense. It can be demonstrated quite clearly mathematically, okay? So take a system like this. This is a classic predator-prey system. Lynxes and snowshoe hares from the records of the Hudson Bay Company, for example. Or alternatively, we might have gophers and coyotes or what have you, right? Here we have some prey encoded with X, and we have some predators, the count of predators encoded in Y. And the fundamental equations are there. The rate of change, the size of the prey population, importantly depends not only on the number of prey around, X, but also on the number of predators around, Y, because predators eat prey. And the rate of change in the predator population depends not only on the number of predators around, Y here, because predators die at a certain rate tau, a certain rate delta, but it also depends on the number of prey around, X, because predators have bigger litters if there's more prey around. The fact that these two are entangled in this way is more or less clear if you understand these equations. But what's less obvious is that it actually tells us something about how these two are connected in the way of the whispers of prey being encoded within the count of predators. So the whispers of the number of predators being encoded in the number of prey. Particularly if you take these variables here and you simply solve for certain elements, like say for the top equation, we solve for Y as a function of alpha, beta, constants, and X, we get this one here, shown in pink or red, right? We have Y equals alpha X minus X dot, the rate of change of X over beta X. What this is telling us, ladies and gentlemen, is that if we had only X, if we had only a time series X, and we could assess its value at a given point in time and its rate of change, that would actually tell us, and if we knew alpha beta, that would tell us about Y, right? We completely specify why. Using just knowledge of the current value of x and how it's changing over time, we can actually get information about y, the number of predators. Similarly, if we had information only about predators, we couldn't directly observe their prey, we could actually figure out how many prey there were, x, using just the information about predators, using just the y. This is profound in the sense that it's saying if we only have partial ability to view the system, partial ability to observe it, partial empirical data about it, that data is, if it's quite complete, it'll actually tell us what the other elements of the system are. So if we have data about predators, it will tell us about the count of prey and vice versa. Okay, so it specifies how we can compute one from the other. So if we knew what alpha beta were, for example, or gamma and delta down here, we could actually learn what the values of the other variables are. Okay, now we're really in trouble here. These displayed fine on mine, but let's just go fix this up. This is going to be a real issue. Okay, because I think I have others. The fox has shown its tail. Good time for it too. Okay, so just to give you an intuition like this, so what I'm saying is that these two are tangled up. Look, let's suppose we're dealing with predators and prey. If the number of hares is dropping really quickly within a population, the number of prey, equally much so you could say gophers, is dropping, it tells us there's a large number of predators around. If we know the number of predators is rising quickly, the population of the number of predators is rising properly, it tells you there's got to be a lot of prey around, right? There's got to be a lot of the things that they eat around. So this is what I mean when I say that I'm just trying to build intuition for the fact that even if we have an observation only about one part of a coupled nonlinear system, the number of prey alone, it whispers to us about predators. There's something that it's telling us about the number of predators out there if we observe its dynamics closely. It encodes information about, if it, you might think about it, about the number of predators. If we're savvy enough, ladies and gentlemen, to read that information out, we might be able to know something about the number of predators out there, right? And there's various evolutions of this that we could specify. Knowing about the number of lengths, the predators are dropping like crazy. It's probably because there's not much prey around. So one part of it whispers to us about the others. Okay, so some of you may be familiar with the West Nile virus model built in our group a number of years back. Here we had representation of people. Down here on the bottom part, we have mosquitoes, and we had birds elsewhere. I think Winchell's rather familiar with this model. And we have birds, and I haven't shown birds. Okay. And there's some evolution here of the status of mosquitoes, of mosquitoes through various stages of life, eggs and pupae and larvae, and hatching into adult mosquitoes. And there's interactions between mosquitoes and humans and between birds and mosquitoes, because birds serve as the so-called reservoir species for mosquitoes. Okay. So I am just going to fix this up. This is really awkward, and I'm afraid it may afflict a certain number of later slides as well, because I saw this. Okay, here we go. So here, if I were to tell you the number of infected people is dropping rapidly, it probably means the mosquito population or the prevalence of West Nile in the mosquito population is low. Right? It whispers about mosquitoes. if I were to tell you that the rate of West Nile in mosquitoes is rising rapidly, it tells us something about the fact that the prevalence of mosquitoes within birds is quite high. It's got to be if it's going up rapidly in mosquitoes. So in short, ladies and gentlemen, we have this coupling here. Okay, this is really quite horrible. Okay. So it's apparently something about the fonts and a difference on this from mine. Okay. So here we go. Now, a key point about this is that this is also true. So what I've been talking about is for models, right? I've been talking about predator-prey model, and I've been talking about West Nile virus model, and early on I talked about susceptible, infected, and temporary immune, or SIRS, and other case models. But ladies and gentlemen, the profound thing that is going to be brought to the table here by delay embedding, Taken's theorem, that provides our next step in understanding, is the fact that all these things that I'm talking about, how in a coupled nonlinear system, observations of one variable whisper truths about the other parts of the system that influence that variable. That is true regardless of whether we're dealing with a model, regardless of whether we have any clues about what a model would look like, regardless, ladies and gentlemen, of the degree to which we understand the governing factors within the system. This is true. So if we have observations about a coupled nonlinear system and we observe one piece of it, we can use that piece to derive high degrees of insight about the system as a whole. Okay. That piece of information we do have information about encodes information about the underlying system that influences it, about the other pieces of the system. Okay, if we are just savvy enough to elicit it. Now, the fundamental advance within this area was one made in the 1980s by Dutch, I believe it was, applied mathematician Floris Takens. Okay, and what he demonstrated is a profound result. Profound in a way that I would designate few other sort of technical observations. It's in a class of most extraordinary. And the observation here is, look, if we have a coupled nonlinear system under a broad set of conditions, if we have just a single time series from that system, an observation of the number of hairs over time, for example, or an observation of the number of new infections of people with West Nile over time, perhaps, or the number of people getting sick from measles over time. If we have just an observation about one piece of the system over time, under a broad set of conditions for a coupled nonlinear systems that give rise to that, we can actually reconstruct the structure of the underlying system, where I use structure as a term for the state space. We can reconstruct something that is diffeomorphic to, that can be directly mapped to the state space, that captures the essential features of that state space. Okay, and in order to do this, we take the time series that we do have, and we perform a technique known as delayed embedding with that time series. So we take the time series of the number of prey over time, the number of snowshoe hares that we observe. Or we take the observations of the number of people getting sick from measles over time on a regular basis, on a regular basis, every month or what have you. And we use that and we undergo what's called delayed embedding to build what's called a shadow manifold out of it. And that shadow manifold will exhibit the essential structure of the system that is driving that variable y, that the empirical observations. It'll be a portrait of, it'll show the face of the underlying system that's behind this data. Okay? Not just that one variable, but all the other variables that contribute to it. Note my comment there. We'll come back to that when we come to understand CCM. Okay, so given an observation vector y, the reconstruction here involves showing a space of dimension n. Okay, so given that observation vector, what's going to happen, ladies and gentlemen, is that we are going to take observations from that vector. So for a given point in that vector, we are going to create, in this long observation vector, for each point in time, we're actually going to create a vector, okay, for that point in time. So if we have a time series here, over time we have, I'm a computer scientist, so I'll write y0, y1, y2, y3, etc. For a given point in this time series, we are going to create a vector. Okay, so let's consider this index 2. If we have tau equals 1, we'll create a vector consisting of y2, the value at that point, y2 minus tau, or 2 minus 1, or 1. I'll just write it as y1, and y0. Okay, that's a vector, and it's a vector for this point in the time series. Okay, and for this point, y of 3, I might create a vector consisting of y3, and y2, and y1. Okay, that's a vector. Each of those is a vector. Okay, so conceptually, for each point in the time series we're dealing with, call it y, we're constructing a vector. Modulo, I mean, ignoring sort of boundary effects where we can't create it because there aren't enough elements or what have you. And so we create from this time series a set of vectors in what's called the E space. Okay, I should really, to be consistent with our label, our other labels, I should probably have called this E times, or actually E minus 1 times tau here. Okay, so we're going to create vectors from this, and we'll populate the space with those vectors. Okay, this is I actually went through and fixed these up earlier, and somehow it doesn't seem to stick. It's quite horrendous. Okay, and let's just see if we can fix this up. Good. Okay. Good. Okay. Sorry about this, folks. I will. We'll try to fix that all up. Okay. So often when we do this for a vector, when we create this, we take a vector, and for each of its elements, ignoring the couple lost through boundary conditions, we create vectors. Often we first undergo a form of data conditioning. So we take the original vector and we create a first differencing of it. Okay. So for example, we'll take that original vector, and before we perform delay embedding, we'll replace, instead of having y0, y1, y2, we'll just have the difference between successive values within it. So the first value of the first difference vector will be y1 minus y0. in the original vector, the next element will be y2 minus y1, the next y3 minus y2, the next y4 minus y3, all the way up to the end. Okay. So that's called first differencing the vector, and that's very common. And that reflects the fact, you may remember that before, when we were reasoning about this, often our reasoning required thinking about the change in something, not merely the number. So, for example, if I know the number of hairs are dropping rapidly, that's about the rate of change. It's not per se about count of hairs right now, it's about the rate of change. And it's that which tells us about the number of links around, the number of predators around. And this is what we get through first differencing, something that here gives us something about the rate of change here. Okay, so often we'll engage in first differencing, as we'll say, as we'll see about these variables, not merely work with the variable itself, but with the first difference of it. And it turns out that this is desirable for reasons that some of us have talked about on other occasions. This sort of first differencing has many virtues to it. It reduces autocorrelation, cases where you have a high dependence of the current value based on the last one, which is very typical for stocks. If I know the value of the stock now, it's probably somewhat similar to the value of the last time, because all that's been changed is the result of a flow. And so by subtracting those two, I can focus on the change in the stock, which is the thing that's affected by other variables, rather than the stock itself. Okay. Okay. Hello. Yes, I'm giving a lecture. What's that? I'll call you after it. Okay. Oh, okay. Fine. One thing is it reduces autocorrelation. The second thing is it can help reduce the unnecessary effects of trends and sort of spurious correlations. Sugihara further suggests that it can allow us to better recognize underlying attractor dynamics, which may be a reflection of these two components. Now, I happen to argue, and this has been borne out to a degree by my many empirical experiments with ground truth data, that we should perform first differencing when we're cross-mapping from a state variable, but not to a given state variable. And we'll come back to this. But when we're trying to understand how y impacts x, we should be often doing it delta x cross-map y. We'll come to that. I haven't introduced cross-mapping yet, but just be aware we don't do it in all cases for most of our work, but only for the left-hand side of cross-mapping. And that will be talked about more in the next lecture. Okay, so let's consider a particular complex system. Let's consider the Lorenz Attractor. Okay, the Lorenz Attractor here is a complex system that's been well studied. It was first identified, if I'm not mistaken, by Feigenbaum in the context of atmospheric physics. Feigenbaum was a professor at MIT who was looking at atmospheric convection, I believe, the sort of ways in which you have a mixing of layers of the atmosphere. And he was studying a system which is a great simplification of atmospheric systems to help ease analytic tractability and insights. And this system has three components, X, Y, and Z. And I've shown here, this is a slide actually from some of Amin's work, a time series for X, Y, and Z up here on the right. Now, we can go and plot out, given observations of X, Y, and Z, if we were to have empirical observations of each of those, we could actually plot out pairwise elements. For example, the so-called phase plane. From each of these, we could plot out, for example, X versus Y, or X versus Z, and Y versus Z. And you'll note that all of them involve these kind of intriguing structures to this. It's a fractal structure, in fact. It's a fractional dimension. But if we were to plot out x, y, and z in a three-dimensional space, we would see something like this. Okay, we would see an underlying state space. Here, these are the elements of state, x, y, and z. So this is technically the full state space. We would see that it has a structure that is whispered at by each of these pairwise reconstructions. More intriguingly, though, ladies and gentlemen, this is based on perfect knowledge of x, y, and z. We have gone and drawn this out. What's more intriguing is that if we were to empirically plot out not x versus y, not x versus z, and not y versus z, but x versus previous x, the value of x versus the value at x from tau time ago, we would see something that looks like this, which is, you might recognize, very similar to the underlying state, the underlying space. Or if we were to look at x t versus x, so along one axis, x of t, along another axis, x of t minus tau, and along another axis, x of t minus 2 tau, just exactly going back to this. This is the sort of reconstruction of the vectors. If we were to plot out for every given point in time, the current value, the value of time. So if we were to plot out a vector whose elements are the value at the current time, the value at tau time ago, and the value at 2 time ago, and we were to do that for successive periods of time, we'd get something that looks like this, which is only shown in a very crude way here because it's a three-dimensional structure. But if I were to go move it around, what you'd recognize is it's very similar in structure to this. It's diffeomorphic to this. In other words, ladies and gentlemen, here we're taking x alone. We're taking a single observation, a single time series from this complex system over time, a complex system that involves many underlying elements of state, three underlying elements of state from a single vector over time of observations. We can reconstruct the underlying state space of the system. We can reconstruct something that's directly just stretched version of this guy here. Okay, and that's what I was saying earlier. That what Taken's theorem says. It says, look, if you have one of these coupled, tangled, nonlinear systems, and we have an observation of just one piece of it, it whispers to us about all the factors that are driving it. And that's what's going on here, ladies and gentlemen. That one set of observations, X, whispers about us for the whole system that's behind it, the whole system that's driving it, the whole system that's governing it. And it's nothing special about X alone. This is not a particularly, special case. If I had done it from Y, I could have gotten the same sort of thing. If I had done it from Z, I could have done the same sort of thing. From an observation of one variable, because the system is so tangled, it tells us a lot about the rest of the system. Just like the number of hairs right now, and the change in the number of hairs right now, and the fact that it's falling quickly tells us about the number of links out there. Just as if the number of links are shooting up, it tells us there must be a lot of hairs out there. So it is in general with these sorts of systems, that an observation of one part will tell us a lot about the other pieces of the system. And the savvy way in which we elicit that is through this delay embedding. So for each point, if we want to reconstruct the underlying system that's governing Y, we take each point Y and we turn it into a vector, this special vector based on delay embedding. Delay, this tau is called the delay for the embedding. And we create for each element of that vector, ignoring sort of the boundary issues, we create vectors themselves. And if we plot out those vectors, we have something that essentially captures the structure of the state space of the system, of the factors that are driving this particular variable y. Okay? Okay. So that's the essential idea behind delay embedding. And if we were to look at a small piece of the time series, this is from some of Amin's work with his tool, and we were to consider, for example, just x here, and we were to create, based on these observations x, we were to create a representation, a delay embedding, a so-called shadow manifold. That's what this is called. When you do this delay embedding, the collection of these vectors is a shadow manifold. Okay, and it's a shadow manifold in this case constructed from x. At a given point of time within x will correspond to a set of points here within the shadow manifold, sort of a set of the trajectory within the shadow manifold. X as a whole is arcing out a trajectory in this underlying state space, and a given subset of that trajectory within X, a given subset of the elements within X, arc out a sort of a sub-trajectory within this overall trajectory. Okay, so this period of time is indicated by this sort of region of it right there. And in general, time series form a rich and potent source of information for doing these embeddings. So these are some more from some of the work that I think this may be from Anahita and Shayan's work, but where we, from a long time series, can reconstruct elements of state space using embedding. So here we have x along this sort of axis at 45 degree, and x minus tau, and then x minus 2 tau on the sort of the other axis, and we can see this trajectory in this reconstructed state space, or so-called shadow manifold. Okay. So when we undergo delay embedding in this sort of way, when we take a potentially conditioned time series, potentially after conditioning, and we do this delay embedding, turning each point in it, each element, each index into a vector, and we place them in a space, we call that space the shadow manifold. Shadow, it's kind of the shadow of the underlying system that's driving this variable from which we're reconstructing it, in this case, x. And this is illustrations of shadow manifolds here. Okay. Okay. So, ladies and gentlemen, okay. This is quite horrendous. Okay. And here we go. There we go. Great. So, ladies and gentlemen, I'd like to talk about this value tau. What is this value tau doing? What is it? What's its function here? If we were to change it, what would we expect? Well, let's think about this. Okay. So tau is specifying for us sort of the spacing between these elements that go into these vectors that we make up. So I've shown here on the board, when I had an original time series y0, y1, y2, y3, if we had tau equal 1, then we're drawing to do the delay embedding and construct these vectors from each index of the time series. We're going to do them from adjacent elements of the vector because tau is 1. So we might extract from this point with y2, y2, y1, y0, right? And from the point with y3, y3, y2, y1. The fact that these are successive numbers, 2, 1, 0, the first one, or 3, 2, 1, is because tau is 1, right? We're drawing things from successive points within a successive indices within the vector. By contrast, if y were 2, we'd be drawing it from every other one, or y is 3 from every third one. And it turns out that this has pretty big significance for understanding what's going on. If we have y equal 1, suppose that we are sampling an underlying dynamic system only rarely, very, very frequently. So we're measuring, my blood sugar in my bloodstream every quarter second, right? Or suppose that we are measuring the number of people currently in a hospital ward every second, right? Or suppose that we are measuring the number of hairs out there in the population. We're getting numbers of that every half day or something. Each observation within that time series is going to be pretty similar to the last one, right? So my blood sugar is not going to change that quickly. If I'm doing that every quarter second or something, there's going to be many readings in a row, which are probably going to be identical, subject, putting aside measurement noise, before I get a significant change, right? If I look at the number of people in the hospital ward and I'm doing that every second, there's going to be a lot of readings which are going to be the same before it changes by 1 or changes by 2. In short, if we do that and we do this delay reconstruction with tau equal 1, we're looking at successive elements of the original time series, x2 and x1 and x0. If those define the coordinates along this, if we're reconstructing this in this shadow manifold, and each axis is x of t minus tau, and x of t minus 2 tau, then a lot of the time x of t, x of t minus tau, and x of t minus 2 tau will be the same. It'll be the same value. Same number of people are in the hospital ward, this second, the last second, and the second before that. So there's going to be a huge number of points here along the diagonal, because you're going to have a huge number of cases where the value along each coordinate is the same, because it's the same successive ones, right? Do you appreciate that point? That if you're reconstructing these from successive values, if the original time series, and the number of time series is a huge number of repeats in it, your reconstruction, the vectors you're going to build during delay embedding will have, if they're in space with 3 dimensions, each of their coordinates will be the same. So they'll be along the diagonal a lot. And, occasionally you'll get this and they'll go slightly off the diagonal, but then they'll come back to the diagonal. What you're going to get is a lot of action going back and forth along this diagonal. And as the number changes, you're going to get it going up and down, but it's not really going to fill the space very much. It's collapsing it almost to one dimension. It's collapsing it close to one dimension within this 3-dimensional space. But as we grow tau, as we take a look not at every point, but at every other, or at every fourth one, or at every 8th one, or at every 16th one, now, ladies and gentlemen, does the data bloom. So we have something that's essentially one-dimensional here. If we're sampling it very quickly, it's essentially one-dimensional. And as we go to larger and larger tau, we'll see something that's more fulsome, something that's more expansive, something that occupies the space in a more complete way. Do you see what I mean? Yeah. So here we're getting it to occupy the space progressively, because we're taking things off the diagonal. Because if we look every 16th element, maybe it's not so likely that they'll be the same value anymore. Or, for the extreme examples I took, instead of looking at the number of patients in the ward every second and using successive seconds to reconstruct the vectors in this delay space, if I were to look at every 6 hours or something, then I would get a lot of differences. It's different. So it's not just going to be on the diagonal; it's going to be in other elements. And this is from data from a model, and you start to see trajectories in state space, etc. Okay. Yeah. Question. No. Typically, it's done for a continuous variable. Uh, yeah, you could say that. It's as we I suppose that's fair to say. Yes, within this embedding space, you're better characterizing the variability if you are dealing with a situation. If you're dealing with a situation where the original time series X is sampled densely. In other words, if you're dealing with it where you have very frequent measurements compared to how quickly the system itself moves. In other words, so I gave the example with blood sugar. If I'm measuring it every quarter second, that's very fast compared to how quickly my blood sugar adjusts. If I'm thinking about the hospital ward and I'm observing every second, that's very quickly compared to how quickly it adjusts. So if it's sampled densely, then having a larger value of tau brings out some of this variability more and allows it to occupy the space. By contrast, if it's sampled sparsely, if we're sampling my blood sugar once a day, or sampling it every 6 hours, or sampling the number of people in the ward of the hospital every fortnight, every 2 weeks or something, here we really don't want a large tau because already we're getting a lot of variability between the different data points. We don't have a lot of these repeats, etc. And what tends to happen there is this is already a system which we're not really sampling it very densely. And as we grow tau, the space will grow more and more twisted. I don't have a better way to describe it, but this is it's getting more and more sort of twisted. Now, this still exhibits an underlying mapping to the space. It just sort of stretched in certain ways, but we really don't want a large tau here. We don't need a large tau. But if it's sampled very densely and you have a lot of repeats, then generally you want a larger tau. Okay, now it turns out there's many uses of the embedded space. Okay, here. And one of them is you recognize hidden structure behind the time series. This is some of the earliest work with delay embedding, was basically using it to reconstruct the governing factors shaping what otherwise seemed to be a random process. They actually plugged in data that seemed to be random. I think it was in one of the first experiments, the timing of drops from a sink in one of the researchers' offices. They sort of plugged in. The drops seemed to occur kind of with no particular pattern. But once they plugged it into a system like this, they actually saw, oh wow, there's actually a huge order behind this. There's a lot of structure behind this, what seems like random data. Same thing with the Lorenz Attractor. This attractor back here, you could look at these time series and you'd think, well, they're kind of random. They're random. In fact, they're not random. They're chaotic, which is a very different thing. They're totally deterministic, subject to round-off error. But they have a lot of order behind them. There's a secret order to this. There's a secret structure, which if we can tease it out, can point us to certain truths about the underlying system. And that's one way we can use these. Another way is we can use it to assess the dimensionality of the system. How complex is this system that's giving rise to this? To what degree do we really need a complex model, or can we use a simpler model? Because this can point us actually, we're not restricted to 2 or 3 dimensions for these reconstructions. Often we'll do it in 10 dimensions, or 8 dimensions, or 6 dimensions, or something along those lines. And we can assess the intrinsic dimensionality of the underlying system to understand how complex does our system really need to be. We can assess the degree to which there's a certain structure that suggests feedbacks, for example, in the underlying system. by looking at its state space. Looking at state space can tell you a lot about fixed points and help you reason about the changes that you see within within the time series. And I've done a lot of work with dimensionality estimation from these underlying state spaces and used it to argue that in some cases it seems to be a very high dimensional model, but there's some key low dimensional dynamics. Finally, and this is going to be our point for the next hour here, we can use it to assess causality. We can use it to assess the degree to which x time series, a variable x is influencing y and how strongly it's influencing it. Okay? So this is a natural place to pause for a moment. I am just going to go here and I have to apologize because I did get a phone call here. So I'm just going to pause for a moment. I'm going to make the phone call back. It seems could be something I need to deal with, and then I will resume within 5 minutes here, okay? And I'd like you to ponder what I've talked about, okay? Okay, so give me just a second. Yeah, so, hi, what's up? Okay. Okay. Yeah. So thanks for everyone's patience here. Okay, so there we go. Okay, and thank you for everyone online's patience here. Okay, so we're going to continue on now for the next stage of our discussion. So we've just covered a few concepts. We've sort of characterized or helped you recall the basic notion of state space. We've talked about this notion of the fact that in coupled nonlinear systems, knowing about empirical data about just one piece of the system whispers information about the other parts of the system that influence that piece. Just as the fact that the number of hairs is dropping rapidly in a predator-prey system tells us that there must be a number of lynx around, a number of predators around to eat them. Or if the number of predators is, the population of predators is rising very quickly, it tells us there must be a plentiful food source around. So it is with these coupled systems more generally. Finally, we talked about how we could use that fundamental intuition or insight through a rigorous procedure known as delay embedding, advanced and formalized through Flores-Taken's embedding theorem. We could use it to tell us quantitative information about the structure of an underlying state space of a system that's driving a given variable, even if we just have information about that one variable. So given observations from a regularly sampled time series y, say the number of prey within a system, we can, through the use of delay embedding, take the information in that time series, use it to construct a set of vectors, which when placed into a space of a given dimension, has a structure that captures the essential structure of the factors that are driving the changes in the number of prey over time. Okay, so given an observation, a regularly spaced set of observations of one variable, it can tell us about the pieces of the system, the essential structure of the pieces of the system that are driving that one variable. Okay, convergent cross-mapping is a tool for using those fundamental insights to assess causal influence of one variable on another, using just a pair of time series. Given a pair of time series x and y, and I have to apologize, sometimes I capitalize them and sometimes I don't here. I should really be more careful with that. Given two time series x and y, convergent cross-mapping it's a technique for rigorously leveraging the insights we just talked about to determine if a causal relationship exists whereby x influences y, causally determines the value of y, whether y causally determines the value of x alone, or whether both causally determine each other. Okay? So for example, to talk about the cases we used as examples earlier, in a case of predator and prey, this is a case of bidirectional causality. The number of prey influence the dynamics of predators. It allows predators to have bigger litters, for example, and reproduce more quickly. And the number of predators influence the dynamics of prey, because the fact that predators are eating them means that the prey population is kept lower than it otherwise would have been. That's a bidirectional relationship. By contrast, we may have one-directional relationships. For example, mosquitoes, the prevalence of infection in mosquitoes, for example, influences the prevalence of infection in humans for West Nile. But for West Nile, you don't get the reciprocal. You don't get people transmitting to mosquitoes. Whereas you do, in a bidirectional way, of mosquitoes and birds back and forth. Okay? So convergent cross-mapping allows us to assess whether a causal relationship exists, and if so, the strength of that relationship. Okay, in order to do that, we're going to be operating with the shadow manifolds reconstructed from from y, and from x, which we'll name with an appropriate m sub the name of the variable from which they're reconstructed. So when I say shadow manifolds, again, I'm talking about the structure that's created when we perform this delay embedding. Okay. Here, if we have observations in a time series X, we'll create a shadow manifold from it called M sub X, consisting of the delay embedded points, vectors constructed from X, and same thing for Y. And we'll call those M sub X and M sub Y respectively, those manifolds, sort of reconstructed spaces. Okay. Essentially what we're going to be doing here follows a brilliant idea that came out of the work of Sugihara et al. At Scripps Institute, which leverages techniques Sugihara and May from past decades. And it's an absolutely brilliant idea. The essential notion here is that we're going to create a shadow manifold. If we want to assess if a variable y influences x, we'll create a shadow manifold from x, and we will look at using nearby points within that shadow manifold. The degree, let me step back. We'll assess the degree to which we can estimate the value of y using that obtains for a given point using the values of y based on nearby points within the shadow manifold for x. Okay, and we'll specifically look at the degree to which our ability to predict the value of y at that point based on those nearby points, the degree to which that ability to predict it rises as the length of the time series we're considering, the so-called library size increases from which we're reconstructing x. This is the essential idea, but in order to understand this, we need to go into much more detail. Okay, so I want to point out a few key elements of this, because this procedure is hard to get your mind totally around, and it's not, in my view, clear for many people from the original papers or from the supplemental material, the intuition behind it. And I'd like to talk this through. So you'll recall when we create a shadow embedding from a time series, such as those shown on the board here, we use that to create a set of vectors, which we place into this space, and we call it a shadow manifold reconstructed from that time series. So if we was time series X, we'll call it the M sub X. Okay. Now, this reconstructed time series, or this reconstructed shadow manifold, rather, this reconstructed state space, rather, the shadow manifold constructed from X, has some very defined features to it. But it's easy when you're new to the concepts to get tripped up on certain concepts. One of the most important things I want to talk about is the implications of proximity within that state space. Okay, if 2 points within that state space are in close proximity, by close proximity I mean that they are located close together within that state space, there's something that means, and that's something that it does not mean. It does not follow. And I want to emphasize this. Points located, if we have an index point P within that shadow manifold, we consider points located around it, which I've colored here in green. This is actually an illustration, I think, maybe from Anahita and Cheyenne's work, or it was from Amin's work, one of the two. So we have index point P shown in red and these points close around it. the fact that they're close around it captures the fact that they're associated with similar state. They have similar values for x of t minus tau, x of t minus 2 tau. Okay, or alternatively, if we think about this as a state space, they're associated with similar state of the system that's driving x. Okay, so they're associated with similar values of state, and they're probably associated with somewhat similar values of x if they're close, because the location here is based on x. But they can be from, and I want to emphasize this very strongly, they can be from very different points in time. Right? So the different points around this red one, these various green ones, some of them could be from far different points than the red one. Some could be from much earlier in time. Some could be from much later in time. Because the system might exhibit, change over time that's semi-periodic, right? We might have something like this over time. And if what we're looking at is x and x minus tau and x minus 2 tau, we might see values which are quite similar to that at many points within this time series, not just for a certain point in time at all. So often these nearby points are from very different points in time. What defines them is that they're similar in state space. Okay, what we're going to be looking at here, ladies and gentlemen, is for convergent cross mapping, is asking for those surrounding points in state space, these kind of points which are have similar state of the underlying system. What are the values of y for those surrounding points? Okay, and the idea here is, ladies and gentlemen, if y is driving x, remember we're trying to assess here, we're given a time series y and a time series x. We're trying to understand the degree to which y is causally changing x. Okay, if y is causally changing x, then within the state space associated with x should be some representation of the current value of y. Remember, the state space reconstructed from x captures the state of the system with respect to the factors governing the value of x, that are driving the value of x. All of that is whispered to us by the value of x. When we reconstruct the state space from the time series x, we're getting a portrait not just about x's state, after all, that's in the time series in a very obvious way, but if the state of the system, of all pieces of the system that are driving x. And if y is driving x, that would imply that the position in the state space, in this reconstructed state space, should tell us a lot about y too, right? So if we're in a nearby position in state space, we should have nearby values of y as well. If this red one is close to this green one in the reconstructed state space, the value of y that obtains at the red one, the value we are interested in estimating with these surrounding points, should be very similar to the value of y at the surrounding points, if the surrounding points are close to this. Okay, they're located very close to us. If y is influencing x, then the value of y at those surrounding points, if we sort of take an average of it, or a weighted average, privileging ones that are closer and weighting less those that are further away, that weighted average should be a pretty good estimate for the value at that red point, the sort of index point around which we're getting these green ones. These green ones are the nearest neighbors within this reconstructed shadow manifold to the red one. And I would argue that if y is driving x, proximity and state space of x should tell us, should indicate proximity and value of y, because that will be part of the state space. And the values of y at nearby points, if we create an estimate from them, a weighted estimate of their values of y, it should be very close to the value of y for the red dot, point around which we're getting these surrounding points. So I'm coloring in my text, because it could be quite dense, I'm coloring references surrounded points with green, and to the index point with red, just like the illustration here is, okay? Now, surrounding points are very close. The value of y at those surrounding points should be pretty good estimate, combined estimate, for the value of y at that point. By contrast, if the surrounding points are not too close, if they're pretty far away in state space, they're probably pretty far away in y as well. So if we have to go pretty far out to find our nearby points, the estimate for y at the red point, at that time of the red point, the estimate from y as generated by these neighbors in state space, not neighbors in time, but neighbors in state space, should be pretty close to the value of y that obtains at the time associated with the red point. Notice what I'm doing here. This is a very important point, and it's a subtle point. I'm asking about I'm trying to understand the degree to which these neighboring points in state space, these points with nearby state, are associated with y that tells me about the value of the degree to which the values of y for them are close to or highly correlated with the value of y at the current point in time. That's the red one, okay? Those nearby points in state space may be from very different points in time. But if y is driving x, the fact that they're close in state space should tell us they're close in y as well. And should mean that they have a value of y that's close to our value of y at the red point at that time. And so it should be very close in value. If those points in state space are very far away, we'd expect that they'd be associated with a value of y that's quite a bit more distant. Okay? Okay. Let's talk about this more. So if we have things that are not too close, we would expect the value of y, the estimate of the value of y at the red point coming from these points in state space, to be cruder than if the surrounding points were very, very tight. We're located tightly around this red point, okay? In this case, we have, if y is driving x, if y is encoded in x's state space, we'd expect these surrounding points to have a value of y very similar to that for this index red point, and therefore to have a really high correlation with the value of y at this index point. Okay. Whoa. Okay. This is horrible. There's something about the font here that's just killing it. And it's something about it not being a true type font. Here we go. Okay. This will just have to do. Okay. Happy. Okay. Okay. So what we're going to consider here, ladies and gentlemen, this is the key element associated with CCM, the sort of key way in which we assess the presence or absence of causality, or the strength of that causality. We're going to consider a library of points of a certain length from time series X, okay? We're trying to assess if the variable associated with time series Y is driving X. So we have a time series X and a time series for Y, okay? Let's consider a library of points sort of a certain subsequence of points from time series X. And at a given, for a given consideration, we'll call this the length of this library L. This library could be, let's suppose L is 3. The library could be the first 3 in this time series, could be the last 3. It could be the 2nd, 3rd, and 4th one. It could be the 10th, 11th, and 12th one. Any of those, okay? And what's going to happen here, ladies and gentlemen, is we are going to consider with this library reconstructing the state space with respect to this library. So we're going to imagine taking that library of points, and we are, so the subsequence of the vector, and we are going to reconstruct the state space. We're going to create a shadow manifold from that library. Okay? So I've told you before how you create a shadow manifold. You take a vector, and for each point in the vector, putting aside boundary issues, for each point in the vector, you are going to build the vector and you know, define that in state space. And that's what we're doing for this library of points, okay? And as the library grows, as the length of the library grows, we're going to be constructing this shadow manifold with more and more points in it, okay? More and more points filling into it, okay? So we're going to go, if we have very small L, we'll have a very sparse shadow manifold. But as we have larger L, we'll have more points within that shadow manifold. We'll be filling in more and more elements of the shadow manifold, more and more elements of the trajectories in it, okay? Now, for a given library of length L, a given library of values Y, of values X rather, we're going to be asking what are the corresponding Y's to these X's, okay? Now, we know we have 2 time series, X and Y, and we actually know for every point in time what the value of Y will be. And we have, for that corresponding point, value at time t, okay? And what's going to happen is, for a given reconstructed shadow manifold here, we are going to have a number of points around. We are going to know, okay, for this index point, this point of interest, call it a point at time t, we know the value of y of t for this one. And since we reconstructed the state space with respect to this library of points, we know the value of y of t. We can find out corresponding values of x for, or excuse me, we can find the closest points within this reconstructed space to this value, to this red value. So we have the red values, value of y of t. We find the nearest points in state space, not the nearest points in time, the nearest points in state space. And for each of them, we get its value y. For each of those nearest points in state space, we get its value y. And then we create a exponentially weighted estimate for y of t based on the values of y of t of these neighbors in state space. Okay, so for each of these green guys here, each of these e+1, where e is the dimension of the state space, we are going to get its value of y of t, and we're going to sum them. We're going to take their average, but we're going to weight the ones that are closer more highly than the ones further in an exponential sort of way. So the weight associated with point will go down exponentially as it's further away. Okay, and critically, we're going to do this, ladies and gentlemen, for each of the points in the library, each of the possible times in the library. So there'll be this one being at the index, there'll be this one here, there'll be this green one, this green one. And for each one of those points in this reconstructed shadow manifold, we'll be asking, okay, how does its true value of y of t compare to the value of y of t estimated from its nearest neighbors in this space? Okay? We'll do that for every point within this, whoa, oh my gosh. Okay, weird things are happening here. For every point within this reconstructed state space, reconstructed from this given library of points, okay? And what we're going to be doing is we're going to, having done that for every index within this library, every legitimate index within this library, we are then going to say, how well does the estimate of the value of y of t at the index point correlate with, using the Pearson correlation coefficient, rho, how well does it correlate with the true value there? So if as we consider each point here, and we consider its nearest neighbors, and we create a weighted average of its nearest neighbors to get an estimate for y of t at the current time, based on the nearest neighbors for that point in state space at the current time, we will then ask, what's the correlation between that estimate and the true value over all the different points in this reconstructed state space? And that will give us a rho. That will give us this rho here, okay? It's defined as the Pearson correlation between the true value for that point and the estimated value, where that correlation is computed over all the legitimate indices of this library of length L, okay? And generally, we're going to be for a given size L, we're going to be actually picking out many different windows of length L. So I mentioned it earlier. If we were considering length 3, we might have our first window be based on y0, y1, y2. That's of length 3, L equals 3. We might also do y1, y2, y3. That's also L equals 3. We might do the last 3. We might do 1,000 random picks of libraries of length L, okay? And for each of them, we reconstruct the shadow manifold. For each point in the shadow manifold, we assess the true value of y and the predicted value of y from its nearest neighbors. And then we take the correlation over all of those in the shadow manifold to get a rho, okay? And we will do that then for many, many different libraries, particular libraries of length L. Just like I said, there's many libraries of length 3, for example. Okay? So questions? Questions about that fundamental picture? Again, a lot of detail here. But let me, again, try to point back. I'm a believer in spiral learning. You come back to a point after a student has heard some related stuff and maybe can fit it in. So the key thing here we want to assess, ladies and gentlemen, is y causally impacting x. If y is causally impacting x, ladies and gentlemen, we would expect here that being close, having if we consider 2 points in the state space reconstructed from X, the shadow manifold reconstructed from X, if Y is driving X, then it's part of the state of the system that's reconstructed in that shadow manifold for X. It's whispered to us by X in terms of the shadow manifold. And so being close in that shadow manifold space. Okay, thanks. I was wondering why it was. So it was being whispered about my sounds of my boot. Okay, so being close in that shadow manifold space as reconstructed from X, in that case, should tell us about the value of Y. It should be similar value of Y. It should be part of that state. And as a result, it should be the estimates of y as garnered from nearby points in x, from nearby points in the shadow manifold for x, should be pretty close in value of y and be a really good estimate. If y is not driving it at all, if y is not driving x at all, then being nearby in the shadow manifold for constructed from x is not going to tell us a lot about y. We're going to have values of y that are quite far off from those nearby neighbors. And taking the average of them is not going to be very meaningful for estimating y. It's going to have a very low correlation. That's the basic idea here. Is x whispering to us about y? We are assessing that through this correlation coefficient rho. We're asking, we realize that that this level of correlation, particularly how it changes, this is the key thing, how it changes as we fill in the space, as we get more and more closer points, it should get better and better if y is whispered to us in x, if the shadow manifold for x is encoding y, as we get denser and denser shadow manifolds with more and more points closer and closer to our index point, to our point of interest, to our y, the one associated time t, the estimates for y of t should get better and better. Okay. Yes. Okay, it's a very good question. As we'll see, so that's an excellent question. As we'll see, though, the key factor we'll be looking at is not just how high rho is, but how does rho change as we consider more points in the shadow manifold X, okay? Because it turns out, and this is what my coming slides are focused on, it turns out it is possible that for statistical reasons, because X and Y are probabilistically dependent to one another, that you could have rho be reasonably high as well. So it turns out that the key differentiator between the two is looking as the value of L rises, how does rho change? Because if it is a causal relationship, if we have a situation where X and Y are not merely correlated, but where the value of Y is determining the value for X over time, then as we add in more points, in other words, as we grow, have larger and larger L, as we have bigger and bigger shadow manifolds we're considering, rho should be going up broadly over time. It should, over L, as L increases. By contrast, if we have merely a probabilistic dependence of X and Y, I should say they're merely correlated. Like if Z, some variable Z is driving X and Y, so they tend to be high and low at similar times, but Y is not driving X. It's more that Z is driving X and Z is driving Y. In that case, we may actually see a high degree of similarity associated with these nearby points with this index point in terms of the value of Y. But what we won't see is that correlation. We'll see a high correlation, but it won't rise with L. So we have to do it for a bunch of different values for L. And we will see that more in further slides, okay? But excellent question, excellent question. Why can't we just use the largest L and declare ourselves done? In fact, the largest L can give you some pretty good ideas from my experience. Like if you get a value that's close to 1 of the rho, the correlation, um, the correlation coefficient, the Pearson correlation here, it's probably a good sign that one is driving the other, okay? But it turns out to really distinguish between causal and non-causal connections, you want to look beyond that, okay? So other questions. I welcome questions. These are awesome to get questions. Okay. So we're going to look at a number of cases here. Okay. Case one, we have a causal connection between X and Y. So Y is driving X, let's suppose. Okay. Oh my gosh, it looks like Christmas. Okay. Okay, here we go. Oh, that wasn't too bad. Okay. Okay, boom. Okay. So suppose Y is driving X. Oop. That's going to lead to convergence with rising rho as the space fills in. Okay. Basically, you're going to go from a situation like this when you have only a few points. The points are going to be more distant to a situation like this where there's so many points that the nearest E of them, E plus one of them, are right around this. They're very close points in the shadow manifold, very short distance away. Okay. And as we fill in points, the estimates of Y generated from these points get closer and closer to the true value of Y. So here, if we have Y going to X, the correlation between the estimated Y, the correlation between the true values, the one at the red point, versus the one that's estimated from the nearest points in state space, ladies and gentlemen, will rise. As we fill in more and more, as we go from something where they're pretty far distant, we have to estimate the value of Y at this red point from values of Y from these points far away, to a situation where they're very tightly clustered. If Y is driving X, they're very tightly clustered around that. Information about Y is encoded in the state space. We're going to end up having a very accurate estimate for Y based on these surrounding points in state space in the shadow manifold from X, okay? And in the absence of noise here, rho approaches 1 as L goes to infinity. Basically, you're going to have something that is just bang on as you fill in more things here. Initially, you can imagine there's only 10 points in this reconstructed state space, only because L is 10. And you'll get, points, the green points being way all around this thing. And eventually, as we add more points in, they come closer and closer yet. And as L goes up, they'll be really clustered right around it. They're going to have values of Y very, very close to this one. And the estimates we get from those neighboring points in state space, reconstructed from X, the correlation between that and the value at Y of t is going to be essentially perfect. Okay, with no noise. And this is something like you'll get something like this. Okay, you'll get something where as L, this is L along here, the library size, and as it rises, you're going to be getting values of rho from different particular libraries. That's what's shown here. This is kind of a density diagram. So there's some libraries which have lower values of rho. When I say lower, it's still like 85 plus. But most, once we start considering rho of any size, it has enough points to essentially be perfect. And this is essentially correlation 1. Essentially, it's perfect. We have large enough library of points that we can just nail the value of Y of t from nearby points in state space. This is with a causal case. Y is influenced in X. So we could just nail the estimate of Y from these nearby points in the state space as reconstructed from it. Notice for very small libraries, very, very small, sometimes just by chance. It's a very small library. We don't happen to have points nearby and so on. And we can get some smaller values here. But by and large, we're getting a pretty good estimate. Okay, I just want to make sure that the Panopto is still doing okay here. Oh my gosh. Okay. Aiden, could you check if the audio is coming through? On it is. Okay. Awesome. Okay. So this is with causality, ladies and gentlemen. We're filling in this space over time. At first, we have super crude. Here's not so crude, but they're still kind of spread out. Eventually, we get to something where they're just totally clustered around it very tightly because we have enough points here. And as y rises, we have more and more points. Rho is going to go to 1. The correlation between what we estimate and what the true value is for each point considered within the shadow manifold. Okay? That's the causal case. Next. Case where we have no causal connection. There's no probabilistic dependence. No interaction. These are solitudes, ladies and gentlemen. Here. So here, look, if y is not influencing x, and there's no correlation between them, y is not going to be encoded in x. The nearest points in the state space as reconstructed from x are going to have just a grab bag of different values of y. There's going to be random values of y. They're not correlated. They're not speaking to x at all. They're not correlated with x. They're not causally driving it, and so therefore the location in state space doesn't tell us anything about y. These are going to have all different grab bag of different values of y. Their ability to estimate the value of y at this index point, this red point, is going to be extremely poor. I mean, we're basically looking at a bunch of random values of y, random because the fact that these are neighboring state points in the state space from x, if y isn't influencing x, the location in state space has no bearing on y. So the values of y sampled by these e+1 neighbors have really no particular significance in estimating the value of y at this one here. And we're going to get whacked out values of estimates for this y of t at this red point. Ladies and gentlemen, it's going to be a very poor estimate, in short, for this case. And so rho is going to be very poor here. Okay, and filling in those points, going from something like this to something like this, going from very sparse to very dense is not going to help at all, because these points here, right around this, if y isn't influencing x, being very close in the shadow manifold space, reconstructed from x, is not going to tell us anything about y. And if there's no correlation here, these are not going to be correlated. And so we're going to have very, very low correlation between our estimate. We're just something like this, ladies and gentlemen. There's going to be a little bit at the start. You see this kind of fringe on the upper side and lower side, because when you're dealing with very small library sizes, L being less than 50 or what have you, it's just a grab bag of different things. There's a lot of small sample size variability, but as L rises, you're not getting tremendous shrinkages and variability. This is rho here, and you'll notice that essentially it's rho of 0. There's really no correlation between what it estimates the value of y being from these with the actual value of y. It's just a wild guesses with really no significance. So it's basically a rho of 0, and you get sometimes by chance some rho that's greater than 0 and some rho that's lower, but you notice it's all in very small ranges here. Okay, so that's a pretty easy case. Now, this is the case that a lot of people worry about, or will worry about. A lot of people will wonder about. How do you determine causality, distinguish causality, discriminate causality from statistical dependence, merely probabilistic dependence? And the particular case that I want to highlight is this one. Okay, so suppose that we have, for example, some other factor. Maybe West Nile virus is, maybe we're looking at mosquitoes and people, trying to understand if there's a causal correlation. But maybe West Nile virus is caused by bad weather, and so, or if it's really hot, people get it from other sources, and more mosquitoes have it. And we will say, well, you know, we look when there's a large number of mosquitoes with it, there's a large number of people with it. Well, it's not a causal thing. It's from some third factor. It's from some other factor. Or maybe there's a clustering of suicides one day after the next, and we say, well, there could be a copycat effect. There's a causal influence. And someone could say, well, how do you know it's not just that those were bad days in terms of unemployment rates? So it happened to be higher in one day and happened to be higher in the next, and there's no causal relationship between the two. In short, Y doesn't determine X, but Z determines Y, Z determines X, so that maybe when Y is high, X tends to be high. When Y is low, X tends to be low. And it might appear, if you naively looked at it, that Y is somehow determining X, but it's actually this puppet master Y that's in the background pulling the strings. And there's actually no causal dependence. Very common concern. Very common problem with the slides. Okay, so let's boom. Okay. So let's consider three cases here to sort of reason through why this scaling with L is different than the case of causal connection. I'm going to argue that as L goes up, how rho behaves for the case of a causal link is different than how rho behaves for this one. Okay? Okay, so let's think about the case of a very low L. Space here is sparse. Points around the kind of index point of interest in this reconstructed state space, reconstructed from X, are distant, right? Now, here, nearby points to this index point, to this red point that we saw earlier, right? I should really have a picture of it here, just to remind us. Here we go. I'll bring these two pictures down here so you can see them. Look at that; it's still messed up in the other things. We're gonna have to debug this. Okay. Here we go, ladies and gentlemen. So for this case of sparse, you know, things are further away, and if we have a correlation between Y and X, then these things that are further away here are further away in X and further away in Y, basically the values for X for the nearby point here, excuse me, the values of that should be Y from the nearby point are it's like they're not particularly close because these points are too far away. So they're not particularly close to the values of Y at that point. Okay, there's not too many positions within the string. This is for very low L over which to estimate rho between this, so there's much statistical error, and as a result, from both these factors, there's great statistical variability in rho here. Okay, so if we look at this, we'll get, for very low L, great statistical variability here. We have very few positions over which to assess the rho in determining the correlation, and it's going to be very variable, and the nearby points are highly variable. So we'll get a high degree of variability for this case. Now, as we add in L, the space is denser. We have something more like this. Okay. Oh. Okay. We have something more like this. Come on. We have something more like this. So as the density of space goes up, things are tighter. Nearby points are associated with x close to x of t, close to the value of x here. And because of this dependence, we're positing that y is correlated with x. So they'll be associated with y that are correlated with x of t. It's similar to what we see at y given x of t. Okay, so they're pretty similar, but they're correlated. They're not causally interacting. We have a larger number of values of the string L over which to estimate the rho, which is greater statistical reliability of this. And as a result, we have lower statistical variability. What we end up getting essentially is here a value for rho that converges on the correlation of x of t and y of t. In other words, we get something where the correlation between what's estimated with the nearby points for y versus this one here at y of t is very similar to the correlation between x of t and y of t, because we're asking the degree as we're going in, getting these points closer and closer in x values to x of t. We're asking, okay, how does that correlate in for values essentially at x of t as L goes up? How does the value of the estimate from those correlate with the estimate at y of t? So I would argue that it's related to this thing here, this correlation statistically, and essentially we will see variability in rho, or we will have rho that goes to values similar to this, but it won't be rising beyond this. Okay, it won't be rising beyond the basic correlation here. Okay, gosh, sorry. Let me do this again. Okay, so oh gosh, this is horrible. Okay, let's just see if we can bring this up. So when we get this correlation in place, but we don't have causation, okay, we're filling in these neighboring points around this index point. We're going to be getting some correlation observed for sure, but it's not going to be rising towards 1. Essentially, we're going to be taking a look at, as we go from more sparse points to more dense points, we are going to have values of y of t for those points around this that are more and more similar to the values of y of t that obtain when we have x of t. So we're going to be getting closer and closer to the correlation between that we'll observe between x of t and y of t. And here, increase the L, what we're going to see is an effect associated with rho where it plateaus out at some level. The key thing that this differentiates this from before, ladies and gentlemen, is that as we fill in the space, we're not going to get a rising rho, a rho that rises with L. What we're going to get is a rho that quickly reaches, typically in a statistical way, it's going to come down from the top, come up from the bottom often, and it will arrive at a correlation around the appropriate correlation that we'll be seeing, and it will look quite different from this. It will look quite different from this causal case, where we have this sort of rise with L in rho. Here we're going to see a kind of statistical convergence. You see it here as well because of small sample size issues, I believe, and you see it here. This is kind of statistical convergence to a certain rho, reflecting the underlying correlation between X and Y. But it's not an underlying correlation. It's not a rho which rises with L in a pronounced way. Okay. And yeah, Sugihara, I'll leave that there, but I'll just note that Sugihara also talks about assessing convergence by reasoning about to what degree a neighborhood in M sub X, this is in the shadow manifold for M constructed from X, maps to a manifold in M sub Y. A shadow manifold is reconstructed for Y. And if it only loosely maps, then we're going to have low correlation. If it maps tightly, we're going to have higher correlation. And the question is here, how does this change as we fill in points over here? To what degree does it go to a tighter ball over here? So the basic deal we'll use within CCM is to assess this causality X, Y. We'll perform this cross mapping. So we'll reconstruct shadow manifold X for length L, and we will consider different subsets of length L, and we'll assess the trajectory for rho for each of those subsets. And in my graphs here, I've plotted that out. So this is one sample, say down here, where rho was very small from a window of size 250. This is another case where it was very high, but most of the cases tend to fall in here. Okay. And in the absence of noise, Y driving X will mean the coefficient goes to 1. And the stronger the causal connection, the faster the convergence. The key factor we're assessing here is how does rho change as L rises? So here is sort of change in rho as L rises. It should, if it's a causal connection, go up more, go up in a sort of fairly well-defined way. You notice this is just rising with L. This is a causal connection. This is the beaming face of causality. Okay, it just rises with L. This is a causal connection as well. You could see the overall trend rising up. This is a non-causal connection. You could see it's statistically converging to a certain thing. Here, essentially 0, but it's converging. These are all cases of non-cause. There may be noise, there may be correlation, but there's no causation. You could see it statistically sort of converge on something. These are cases of causation. This is kind of a curious one, but it does rise overall after this kind of odd thing. This becomes so tight you can barely see it here. These are indirectly causal, where X influences Y and Y influences Z, and we're assessing X and Z, say. So here, we have the practical need to use this procedure to assess causality. And in my next talk, I'm going to be talking about some tips for doing this. The key is often to look for this sign of statistical convergence in the upper fringe, to ask whether as a whole it's rising, rising with rho. Sometimes it does plateau, but is it rising with rho particularly early on? Or is it sort of converging from above? Okay, this is with very high noise. You'll notice with high noise, the causal cases still seem quite clear, but you notice the indirect causation cases become less clear. If we have weak causation, it can be overridden by noise and we won't recognize it. Okay. This is no noise, direct causality, no noise, indirect causality. Once again, we see a strong causal connection. So bear in mind that if X influences Y and Y influences Z, and you're dealing with two data sets for X and Z, you will see a causal link from X to Z. Even though it operates through Y, you will see a causal link from X to Z, because X does ultimately impact Z causally. It's just it happens to be through a different variable, a latent variable. Okay. One of the things that this brings out, as we'll see in the next presentation, is that operating purely on means, looking at the mean of these graphs, it can be very confusing. Because often what you're looking at that I find most helpful is the envelope. It's the envelope around these graphs. And we have specialized libraries now that we've built up that will allow you to graph out these envelopes in a way that will help you recognize clear evidence of causation. CCM is not perfect. CCM has its limitations. In the context of large amounts of noise, CCM can drown out weak connections. The causality associated with weak connections is drowned out by the noise. This is a high noise case, but causal connections, particularly strong causal connections, can still come through. And that's what you see over here. Although this one is a very weak connection that is direct, and you see it is it's a little bit borderline whether it's causal. These are no longer clearly causal. They were much more clearly causal here. Okay. These are ground truth examples from known situations. Okay. So let me reiterate the basic features of this presentation so you recall them. Number one, ladies and gentlemen, it's the notion of state space. State space is a way of depicting model dynamics over time. Number two, the notion of this notion that when we have a causal, a nonlinear coupled system, the value of any one piece of that system will often whisper to you about what's going on in other parts of the system. Number three, using that insight when we have a coupled nonlinear system, using that insight to go from data about any one piece of the system to go to a portrait of the underlying structure of the whole system through the use of delay embedding. For each point in the data series we do have, we can construct vectors. We put those vectors into a space, which we will call the shadow manifold. And that shadow manifold is provably, for a broad class of complex systems, provably directly mappable into the state space of the underlying system that's driving this. Even if we don't know anything about that underlying system directly, we can do this from empirical data. We can reconstruct salient features, key features of the underlying system that's giving rise to the evidence that we see. Numbers of tweets over time, numbers of searches online, numbers of incident cases. We can use this data to peer into the underlying driving dynamics. Next, using this notion of shadow manifolds, reflecting on how we could use those to assess causality by reconstructing a shadow manifold. If we want to assess whether Y influences X, we reconstruct the shadow manifold for X, call it M sub X. We use that shadow manifold to find nearby point. For each point within that shadow manifold examined in turn, we find the nearest points in that shadow manifold, not in time, but in that shadow manifold, and find the values of Y for them, and check whether the values of Y for those nearby points in the state space of M sub X, in this reconstructed state space reconstructed from X, this shadow manifold M sub X, we assess whether the nearest points have allow us to estimate the value for Y at that index point, the point whose nearest neighbors are being assessed. And the idea here, the key insight is that if X is being driven by Y, information about Y will be encoded in the state space as captured through M sub X. Being close in that state space will mean we're close in Y. But what we're particularly interested in is how does the closeness of our ability to reconstruct Y of t change as we add more points into the state space, into this shadow manifold space, M sub X. If we see a causal link from Y to X, not mere a correlational one, we should see rho going up over time in this sort of way. We should see it rise potentially to very high values, asymptotically to 1 if there's no noise. By contrast, if we have merely correlational components linking Y and X, what we will see is rho going to a correlational value here, reflecting the strength of correlation between X and Y. But because it's not a causal connection, as we add points in, it won't go up towards 1 in an onwards way. So we'll see this sort of convergence from above and below that's merely statistical in nature. Okay, and we can use that to assess the existence of a causal connection from Y to X, and even the strength, the value of rho here, to assess the strength of that connection for cases where it does appear to be causal. And while CCM is not perfect, there is going to be a broad set of cases where it works very well, and particularly cases where you don't have high noise or where you do have strong causal connections. You can get very clear signal out of CCM. For cases where you have weak connections or where there's a lot of noise, and where there's a lot of noise, they can be washed out, and they won't be easily distinguishable from a case of non-causality. Okay, so that's all for this first lecture. Are there any questions about this before I go on to my second lecture? Questions? Questions? Okay, so I'm going to stop this broadcast and go on to the next one.